Today we're talking about uniform circular motion and just section 4-5 for now. So the object in question here is going to move in a circle at a constant speed. That's the definition of uniform circular motion. That's the uniform part, is that it's not changing speed. The object is only changing direction. So the velocity is going to have that same magnitude all the way around the circle. And so you can see the length of this velocity vector isn't changing here, but it's obviously changing direction. This blue ball is going counterclockwise. And then when this happens, the acceleration of the object is always toward the center of the circle. So there's a proof of that, a mathematical proof of why that is in your textbook. There's also a video that you can watch. It's posted on my DSHA that has like a slightly different mathematical proof of why is that the acceleration vector points toward the center. So you can watch that if you're interested in that, but you won't be tested on why that is. You'll just be expected to know that that's true. Okay, so as you're thinking about objects that do this, so you can think about a merry-go-round, you can think about a vertical circle like a Ferris wheel, these types of things, even a car going around a circular racetrack. Those examples can be described as an object experiencing centripetal acceleration. That's a special word that's used to describe this situation. And in this case, that word is just talking about the fact that the acceleration points toward the center of the circle. That the middle of this word here has means seeking or flying, I guess, when I looked it up on the etymology dictionary. So that root word means to seek, and then obviously centra means the center. It comes from the same root word as compete, so the pet part or the pete part is like to seek, somebody else. The com part is with. So then, you're competing, you're seeking or flying at someone else, okay? So that's what I want you to remember. There's a word we're not going to use in this chapter, the F word, okay? That's a centra, and then it ends with another suffix, and that is not a thing that we are going to talk about. All right. Moving on, the acceleration, when we want to know how strong it is, how much acceleration are we talking about? What's the magnitude here? Notice there's no little arrow symbol over that AC, okay? And really, this is just the regular acceleration we're talking about, okay? It's just it's got the little c just because that's denoting that it's toward the center. But we can find the size of that number if we do velocity squared divided by the radius. This formula is on the AP sheet. It's down a ways, okay? So if we know the speed it's going around and the radius, then we've got that. Hopefully it makes sense to you that the smaller the radius, okay, the larger the acceleration. We'll get into force, centripetal force in the next section, and we'll talk about maybe why that makes sense. All right, so then when we talk about a period, that's another measurement we can take of objects that move in a circle. So when we refer to that. Obviously, this is repeated motion. And so the idea of a period is how long does it take in time to complete one of that cycle, or one circle in this case. And so, I pasted in this picture of one of those rides where you can like stand against the wall and they spin it so fast that the floor drops out. Okay, so that would have a period. Once it reaches a constant speed, it would have a regular period. So that would not change. And you could calculate that. You would know the circumference of the circle, for instance, and the speed of a point on the outside edge, let's say. And then you could find that period. Or maybe you know the period and you know the radius and you're trying to find the velocity, or the speed, I should say. Okay. So I'm going to send you to another video to watch this sample problem. All right, thanks for listening.